here we go. So we'll just start there. So we're going to start with increasing, decreasing, piecewise functions. So a definition of a function which is increasing. So a function is increasing on an interval. So we're going to say it's on some interval. And this is always an open interval. So it'll be some x1 to x2 is what we'll write. So if it's increasing, that is if as we go forward or to the right on the number line for the x values, the function value becomes greater. And so this is easier just kind of shown than explained. So here if I have some function, here if I have some x1, here if I have some x2, the function of x1, function of x2. So here, notice that for every point in between these two, right, for this interval here, everything here, if I choose this point and this point, if it's more to the right, it's also a higher value in the y, okay? So that's what it means to be increasing. This is always an open interval. Here, if I'm going down, same concept. Here I'll have my function of x, I'll have my x1, here I'll have my x2. Oops, make that look 2. My function value is always, my function for lower value of x's give higher value y's. And so there's one other one. We can say a function is constant. And that's when x1 equals x2 for some interval. The constant function can be closed, but all the other ones are going to be open intervals, so you can be using the parentheses, not the brackets. And the reason being is it doesn't make sense to say a function's increasing at a point because at a point, I have nothing else to compare it to. So increasing, decreasing is a comparison. So if I'm given a singular entity, I have nothing to compare it to. So we never say it's at a point. And I can show, let me just kind of explain this real quick again here. If I have, let's pretend I have this, right? This point here at x, I don't know, just say 3, right? Here at x3. Notice that every point here, the function's increasing, here the function's decreasing, but at x3 is the function increasing or decreasing? Well, if I'm looking to the left of it, it looks like it's increasing. I'm looking to the right of it, it looks like it's decreasing. So at this point, we just say it's neither. It's neither increasing or decreasing. And so we don't make evaluations at points. Okay. All right, so local mins and max. And so we say a function has a local min value of at f on f at a if f of a is less than all the other f of x around it for some open interval containing a. We say it's a max if f of a is greater than everything around it. Again, this is easier just to explain with the picture. So let's just draw in a picture here. Up, comes down, comes up, goes down, goes up, down, up. So here's some function. This is my some function f of x. It's kind of not the happiest function in the world, but it is a function, right? Let me actually, yeah. So let's just pretend this kind of is a little bit more even. I guess it's okay. All right, so if we're looking at values, notice here that I can say a local minimum occurs here, right? Even though this point's a lot higher than everything else on this side in this little space, right? But in this little open interval from here to here, this is the smallest point. And so I can say that's a local min. Right, so I say right here is a local min. I also can say here's a local minimum point because if I look around it, everything around it, and I also can say this is a local minimum point because notice even though it's for quite a small interval, it still qualifies. And so this, and this are all local minimum points. I can say local max at here, right before it falls off, at here, and here. So these are all local maximums. So here, here, and here. Okay. And so local maxes occur at points. And so you say a point is a local max or a point is a local min, or you can say the function value at something. We'll actually give a concrete example. So here, notice that this local minimum is not close to a global minimum. When I say global, I mean over a whole function, what's the smallest value can occur. So for minimum, be the smallest value. For the maximum, be the largest value. Notice that none of these local mins or max are global mins or maxes because this point is lower than all my other local mins or max. And this point is higher than all my other maxes. And so this one, we're not talking about global mins or max, we're just talking locally. And locally, we only need to be in a very small area, right? As long as it's true for some open interval, doesn't matter how small it is a local min or max. Does that make sense? Okay. Yeah. All right. Thanks. So let's go ahead and do this in practice. I'll do one, and then I'll have you guys kind of try one. And then, so I'll do one, I'll have you guys try one, and then we're going to talk about piecewise functions. And then I'm going to open up the homework and kind of work through the homework a little bit today with you. Just because some of the piecewise functions get a little bit complex, and I want you to see the process of that. On that note, since I'm opening up the homework, I don't think I should make that publicly available on YouTube. So this might be a private video, or an unlisted video. That way only you guys have access to it, and therefore I'm not breaking copyright laws. I think it's okay the other way, but I want to be I just rather be cautious. So that makes sense. So it'll just be unlisted, but you'll have access to it because I'll give you the link to it. All right, so let's talk about this. So here I give you the function. Do you need to really worry about this function? No. Is the computer program going to give you the function? Yes. Do you really need to worry about the function? Not really. The reason we give you the function is that because I can definitively say this is going into infinity and into infinity. I can definitively say that because this is a polynomial, and therefore the domain is all real numbers. Don't worry too much about that. So what we're going to do here is what you're going to do, the same thing you're going to do on the homework, is you're going to say, where's the local minimums, where are the local maximums, and where is the function increasing, where is the function decreasing? Okay? All right, so looking at this, we're going to try to find the points. And so we're just going to guess the points the best we can. So I'm going to guess this point right here is a local min, and I'm going to guess this point right about here is a local max. So I'm just guessing what that point is. The computer's nice. The computer just says that's that point. It gives you the point, so you don't have to worry about it. For something that we're doing kind of on paper, you're just going to guess the best you can, and I usually give a pretty good leeway on what I consider close is. It's usually like up and down, like 0.5 of a point, so it's pretty high. So here I'm going to say this is 1, 2, 3 and a little bit. So I'm going to say like 3.2, comma, and then it's like a little bit higher, but not quite. So like 1, 2, 3, 4, 5, 6 and I don't know, a third. So I'm going to say this is 3.2 and 6.3 roughly. And then over here, I'm going to be negative 1, 2, 3 and a little bit. So I'll say minus 3.2. That negative sign look a little better. And then here I'm going to be minus 1, 2, 3, 4, 5, 6 again, and I don't know, 6.3. Let's just do that. All right, it's a 6.3. So here I'm going to say I have a local minimum at minus 3.2, comma, 6.3. And notice this is a point. A local minimum is a point. It's where it occurs and what the value is. I can also say I have a local min of f equal to, that should be a negative. Sorry about that, guys. F equal to negative 6.3 at x equal to minus 3.2. This is just a more pedantic way of saying it. It's saying, what's my local minimum? Well, this is the value, and that occurs at when x is negative 3.2. this says the same thing. This says the exact same thing. So I've almost used the points. So our local max here is this point. So it's 3.2, positive 6.3. So in this case, so here I've identified my local mins and a max. And the reason I do the mins and max first is because once I know this, I know where my function's increasing and where my function's decreasing. So increase, let me just increasing, and then we're also going to do decreasing. All right, so where's my function increasing? Where's my function decreasing? So here, the function's increasing between here and here, right? But when I grab this, notice here, where it's x in some interval. So we're going to use the x values for our interval. So when we identify an interval, we're always identifying it using the x's. And so here, the x value is negative 3.2 and then positive 3.2. So it's increasing from negative 3.2 to positive 3.2. Okay, so here it's saying when x is negative 3.2 all the way up to positive 3.2, the value of the function goes up as I go to the right on the number line, okay? Then, and also you can, another way of doing this is then between a local min and a local max, the function will be increasing between these two. So here's the min point, here's the max point, it's always increasing between these two. If not, you should have had either another min or max or it's constant for a while. Here, it's decreasing. Well, it's decreasing on two different intervals, from here to here, and then from here onward. And since I know this is a function, my first interval where it's decreasing is from minus infinity to minus 3.2. Once again, here I'm using the x values. Okay, so it's decreasing. You can put a comma here, and that's actually how your homework wants it, or you can use a union. Either is fine. Here it's also decreasing on the interval from 3.2 all the way to infinity. So I like to list my intervals of increasing and decreasing as separate intervals. So it's increasing in this interval, it's decreasing in this interval, it's decreasing in this interval. It's not incorrect to say it's decreasing over an interval union another interval. That's fine, but I like to use commas. In fact, the homework also does. So, all right. So let me just quickly review how to do this again. You're going to find your minimums and your maximums, right? And so, and let me just let me go ahead and label this is my min, this is my max. And you're just going to write down what those values are. And these are points. So give a point this way or this way. Probably give it this way. Then you're going to identify between these mins and max is my function increasing or decreasing. And then you're going to take the x values, and develop and make your interval. So here it's from minus infinity to the x value of negative 3.2. And then here it's from 3.2 all the way to infinity. So that gives my intervals. You can separate your intervals with commas or unions. The commas are more common because that's you're talking about intervals as separate entities. So now that I've done it, I want you to give it a try. So given the following function, so this is just some really weird function I made just to make it fit on this graph nicely. All you have to do is just quickly identify as best you can the points of increasing and decreasing, or your local min and max. Then after doing that, so I really should swap what I ask you to do. I should say find local min and max and then identify the intervals. Go to find the local min and max, guess the best you can, right? And then identify the places of increasing and decreasing on your own. And then I'll give you guys about 2 or 3 minutes to try it on your own. And then I'll start asking for answers. But the process of trying to do it, you'll figure out where your trouble points are. Maybe where it's like, well, I'm not understanding this as much as I'd like. Okay, so give it a try. And then I'll ask for it in a second. Does it matter how you draw examples 1 and 2. No, as long as there's some increasing and some decreasing function, you're good. Ah. Oh yeah, let me fix that now. It's probably because when I called out your name, you didn't respond, so. All right, so let's go ahead and get some answers for this. All right, so what do you guys have for the local minimum? Or minimums, there might be more than one. Oh, I saw that. Okay. Isn't it great when you actually hit the wrong button? It's even worse when you're sending text messages, right? It's like, I didn't mean to say that. Okay, so the minimum. So here, yeah, so, okay. So let's see what we got here. So we guys have, I have -4, 0, -3.5, 0. So let's look in here. So here's -1, 2, 3, 4. I think 3.5 is a little bit more accurate. So I'm going to use that one. If you said -4, it's not fine. I mean, if I like zoom way in, right? Like it all looks about the same, right? So once again, you'll get some leeway. When we actually do this on the homework, you get a point. So it actually gives you the point, so you don't have to worry about it. So I'm going to say this is -3.5 and 0. So this is -3.5 and 0. I'm going to just label it here just for the sake of teaching. And the other one you guys have is 7 and -6. So 1, 2, 3, 4, 5, 6. I don't count the first one. 1, 2, 3, 4, 5, 6, 7. Yep. And then -1, 2, 3, 4, 5, 6. Yep. That looks good. And that's close enough, right? So we'll say the other point here is +7 minus a 6. Let's see if I can keep my. Okay. There we go. All right. And so what's our local max? Yeah, 0, 1 is correct. And so here's our local max at 0, 1. Okay. So we have now, once we have our points identified, we're going to have intervals of increasing and decreasing. Let's put those in. All right. So what do you get for the interval of increasing? You actually have 2 intervals for each. So what's the interval of increasing, or the 2 intervals for increasing and 2 intervals of decreasing? Let's start with increasing. Increasing from, yeah, so if you had -4 before, you're going to have -4 again. I'm going to use 3.5 just for the sake of the notes. So if you have -4 on yours, you're good to go. Don't even fix it, right? So here we have -3.5 to 0. And then from 7 to infinity. All right, so notice between the min to the max, this is, we're going to take the x values. And then from the x values from here on to infinity. And then decreasing would be the same thing, just backwards. So it'll be minus infinity to negative 3.5. And then from 0, because the x value, 0 to, from a max to a min will be decreasing, from 0 to 7. All right. And so, okay, so everyone see how these numbers came about? Once again, you're just going to find your points of local min and max. So just kind of label them. And then you're going to take the x values. If it's increasing between the 2 points, you can just say this x value to this x value. So once again, x value, x value. And then if it's going off the page, but you know it goes to infinity with the arrows, you're going to just say 7 to infinity. These are always parentheses. You never use brackets here. Okay, so always just use parentheses. And that's how it goes. All right, let's talk about a piecewise function. Some functions are defined piecewise, which use different output formulas for different parts of the domain. So basically, a piecewise function chops up the domain into a lot of different things. So, and the domain, I remember what x values you plug in, and then has different functions for the outputs for y values. We'll do 2 here. We'll do another 2 on the from the homework. And we'll go from there. So here's an example. Say I have a cell phone plan that costs $59 a month and comes with 500 free minutes, and charges 10 cents after every minute for every minute after that. And so in this case, I'm going to say X is my minutes, X is number of minutes I used, number of minutes, and then C is the cost, right? And this is the cost in dollars. And so I develop a function. So here, between 0, because I can use no minutes, I can have a cell phone plan and just never call anybody for a month, or I can use up to 500. It's going to cost me $59. And then after that, anything above 500, I'm going to have to take 500. I'll take whatever minutes I use minus 500 because already those are free, and then I'm going to have to pay 10 cents per number or per minute, and go from there. So here I'm just going to evaluate this as a couple different things. So when I use 258 minutes, how much does my cell phone plan cost? So I'm going to write this a little bit. X is the number of minutes. Number of minutes. Yeah, so yeah, this one costs $59. And when I use 500 minutes, how much does the cell phone the plan cost? $59. Now, if I use 302 minutes, what does my plan cost at this point? Well, at this point, I'm not using this one anymore. I'm using this one because that's where my X lies. And so here would be $59 plus 0.10 times 532 minus 500. What does that equal? Well, 532 minus 500 is just 32. 32 times 10 is 3.2. 3.2 times 5, 59, which would be $62.20. Because this is $3.2. Okay, and so here the X is here, plug it into here, we get 59. Here the X is here, plug it into here because this is the equal sign, 59. All right, so let me talk about something a little bit odd for a second. It's used in this chapter. I don't know if it ever comes up in the exams or the homework, but it was taught in the chapter, and I figured I might as well just touch on it real quick. It's a piecewise function. It's which breaks it up. Its domain infinitely in some sense. And so here's the greatest integer function. The greatest integer function is this. It's just a double bracket on something. And it is equal to the greatest integer that is less than or equal to x. And so this is just easier to stream by example. So if I have 2.1, the greatest integer for that is 2, right? It's the greatest integer which is less than or equal to. So 2 is less than this. And notice 2 also will go to 2, which is equal to x. So it's the highest integer, or the most to the right on the number line. That's equal to this. And then say if I had 2.7, that'd also go to 2. Here, if I had 5.8, that'd go to 5. If I had 5.1, that'd go to 5. And if I had 5, that goes to 5. Where it gets a little bit odd is if I have a negative 2.3. Negative 2.3, if I'm looking at my number line, right? Here's minus 2, here's minus 3. And if I'm at negative 2.3, so I'm right about here, the greatest integer, which is less than that, is actually negative 3. So this goes to negative 3. And same thing here for minus 2.8, that'd go to minus 3, and negative 3 would go to minus 3. Same thing if I had negative 1.7, that'd go to minus 2. If I had 0.1, that'd go to 0. And so it's just, so basically you're always just kind of rounding down. Does that make sense? So whatever number it is, round down. So here, rounding down isn't rounding to negative 2, it's rounding to negative 3 because it's more to the, it's the first integer. Basically, if I walk left, that's the first integer I hit. That's what I'm doing. So here, if I'm at between 2 and 3, and I put in the value of 2.1, I walk to the left, is the first integer I hit. If I'm at 2.7, I walk to the left, is the first integer I hit. If I'm at between negative 5 and negative 4, if I'm at negative 4.8, oops, negative 4.8 would be over here. Sorry about that. That'd be like 4.2. So 4.2, if I walk to the left, the first integer I hit is negative 5. Okay. Now the reason we go over this, because it makes a really almost all introductory college algebra books go over this in some form. And the reason is it makes a fun little thing, because here if I graph this, I'm a solid line because at 0 I am 0, and then all the way, all the numbers, integers, all the numbers up to that would go down to 0. Here I'm at 1, and it's open circle. Here at 2, I am 2. According to this, right? At 2.1, I'm still 2. At 2.7, I'm still 2. All the way up until I hit 3, because once I'm 3, I am 3. And it goes up and comes in like this. Same thing here. So this would be at negative 1, I'm negative 1. And then at negative 2, at negative 0.5, I'm still negative 1, because that's to the right. And so you just have this really interesting piecewise function. This goes on forever this way and this way. Okay, so it's just something we kind of go over and teach for a second. All right, so let's graph this one. So let's graph this. So notice here, my value is, so x less than or equal to 2, I'm going to be x equals square root of 2. So here, so f of, let's just say negative 2, I plug that into this one. So it'll be minus 2 squared, which gives me 4. F at minus 1, that's going to be minus 1 squared, because I'm still in this domain, because I'm still less than 2, is equal to 1. F of 0 equals 0 squared, which is equal to 0. F of 1 equals to 1 squared, which is equal to 1. F of 2, notice 2 is still in this function, so I'm still using the x squared, is 2 squared is equal to 4. And then f of 3, once I hit f of 3, I'm using this function because x is greater than 2. So be 3 minus 2, which is equal to 1. And so we kind of fill this in. And the way we do this, I do want to know what this function is at 2. So say I was at, so let me just type in the function of 2.00001. Well, that's slightly above 1. So that's going to equal to be 2.00001 minus 2, which is about 0.00001. honestly, what I honestly do in my head is just plug in a 2, figure out what the number is, and just put an open circle. So if I put 2 in here, I get an open circle at 0. So let's go ahead and graph this point. So here I have at -2, I'm 4. 1, 2, 3, 4. Here at -1, I'm 1. Here I'm at 0. Here I'm at 1. Here I'm at 4 again. And notice here at 2, I'm still part of this function. And so from minus infinity comes in, comes here, and hits 2. It stops right there. Then, once I cross over this threshold, I become an open circle here. And then at 3, I'm at 1. And at 4, I'm at 2. And then it just becomes this linear line right here. And so here I've graphed this. Okay. Why'd you start with -2? Just to start somewhere. I figured I'd just start from -2. I wanted to graph my parabola because this is a parabola. And then I also wanted to do my line here. And so I figured -2 would give me enough points to graph my parabola with you guys. Technically, I can do -3, negative up to infinity. This function is defined everywhere. So